Hello everyone, welcome back to our channel. In this video we'll continue this problem, that is LeetCode 958, check completeness of a binary tree. But in this video we'll solve this question with a DFS approach. Here we have to return whether the given tree is complete tree or not. Okay. Now the question comes that how to approach this question with a DFS type solution, or how the idea clicks that this is the correct way to approach it. So firstly, I'll ask that if I want to store a particular tree in an array, how can I store it? Like for ith node, for a particular node, if I store that node at the ith index of an array, then what position would it be its left, and what position would it be its right node be storing at? If I store a particular, I'm using one based indexing, that is I'm storing from first index, not 0th index. Okay, in this case, if I store a particular node, a tree node at ith index, then its left node will be stored at 2 into ith, and right node will be stored at 2 into I plus 1 index. Okay, so this you should know this one thing. If I want to store a tree in an array, and if I store ith index at a particular index at ith position, then its left would be at 2 into I and right would be at 2 into I plus 1. This is the case for one based indexing. Okay, now let us do a dry run on this. How can I store it? Okay, for this tree I'll mark it as, I'll name them 1 2 3 4 5 6 7, this is 8 and 9. Okay, now I'll start storing. I'll make an array. I'll name the indexes, that 1 2 3 4 and so on. I store the root node at first index 1, and what if and now I have to store the left and right child. Then if it is at 1, this would be at 2 into 1, that is 2, and 2 into 1 plus 1, that is 3. I will store 2 at second index, 7 at third index. Now for this node, its left and right, it is at 2, so it would be 2, that is 2 into I, that is 2 into 2, that is 4. Here it is 2 into I plus 1, that is 2 into 2 plus 1, that is 5. At fourth I'll store 3, at 5 I'll store 5, 3 and 5. Okay, now regarding this node, now this node is at fourth, left would be at 2 into 4, that is 8. This would be at 2 into 4 plus 1, that is 9. 6 7 8 and 9. What are these? These are 4 and 6. Let's store 4 and 6. Okay, now these nodes do not have any left right, these nodes do not have any left or right. Now I'll store this. It is at the position of third, index third, so its left will be stored at 2 into I, that is 2 into 3 6. It will be 2 into 3 plus 1, that is 7. 6 and 7 8 9. So you can see I have stored all the nodes in this tree in an array. Now I'll count. Now I'll ask that what is the last index at which the node is stored. So it is the 9th index. The last node is stored at 9th index. Okay, 9th index. Now I'll count the number of nodes in the tree. It is 1 2 3 4 5 6 7 8 9. It is 9 number of nodes. So you can see that it is a complete tree. Yes, I can see it is a complete tree. So for a complete tree, the last index where the node is stored will be equal to the total number of nodes in this tree. This is a very important point. And on this basic idea, our DFS approach will be based on. That is, if the last index will be greater than total nodes, in that case I will say not a complete tree. Or if it is equal to or even less than, there will be a case less than but not greater than. Otherwise yes, it is a complete tree. So this is a basic idea. Now I'll write the code of this problem in DFS, and then we'll do a dry run. Okay, so first I will write the main function. Like this is the main function. So in the main function, first we will count the total number of nodes, right? We'll make a count node function, and for making this function, I had made a previous video that how to count the total number of nodes. You can watch that. So in this I'll simply return the root node, and this function will return with the integer value, that is the count. Now in this I will call the solve function, and this solve function is the DFS of the DFS of this problem, this 958. I'll make this function. Now in this function this function will return a boolean type. In this function I'll pass what parameters, root, then this one is the index. I told regarding that we will be using one based indexing, so I have passed 1, that store root at the first index, 1 index. Then another is the total number of nodes that we have counted in the count variable, count. So this is we have to first maintain in the main function. Now we will write the solve function. Now we will write the main function, the solve function. As I told, the return type would be boolean. Now I'll name the function as solve, and I have passed 3 parameters, that is root, then index, I'll name it as I, then total means the total number of nodes. Okay, now the base case is, for example, if root is null, then do what? If root is null, I can simply return, if the root is null, I'll return true, because like for example, if I say that there is no node, if there is no node, we can say that it is a complete tree, right? Now I'll write the condition that I told. If the index is greater than this, the total number of nodes which we have in the tree, in this case I'll return false. Then I'll call the 2 recursion calls for left as well as for right. Now I'll do solve, then root dot left. For left child, it is stored into 2 into I, and this total remains the same. As well as now I'll do and because I want, like, if any of the recursion call will return false, then the final answer will be false, because the tree should be completely correct, not like if the tree is complete in the left hand side but not in the right side, then that doesn't matter. The tree should be completely correct. That means the tree should abide the rules of a complete tree from everywhere, in the left side as well, in the right side as well. Okay, that is why I wrote and return solve root dot right. For right child we store it in 2 into I plus 1 and total remains the same. So that's it. This is the entire code for DFS of this problem. Now we'll do a quick dry run. Okay, so this is an example. Clearly we can see that this is a complete tree, right? Now we will check this by a dry run of this. So I have called this function solve function. First I'll make a count of total, that is 1 2 3 4 5 6 7 8 9. There are total 9. Now I'll make an array. 1 2 3 4 5 6 7 8 9 10. Okay, now right now what I'll do, I'll call this solve function with this and with I equal to 1, right? I'll name these as A, B, C, D, E, F, G, H and I. Now I'll call this solve function with A and I equals to 1. It will check does this A equal to null? No, it is not. Now it will come over here. Now I at A is 1. If 1 is greater than 9, no, come over here. Now it will call solve towards left. It will come towards left with 2 into I, that is 2. I here is 2. Now for B it will check this, is it B? Is B null? No. If 2 is greater than 9, no. Do what? Call left. Okay, it comes over here. 2 into I, that is 4. For D it will check, is D null? No. Is 4 is greater than 9? No. Now check what? Check this. It will call root dot left with 2 into I, that is 8. It comes over here at H. It comes at H. Now at H it will again check, is H null? No. Is 8 greater than 9? No. It will call root dot left. It will come over here at last. At this position it will hit this base case that this is null. Okay, this is null, return true. Then return true. It will come over here. Now it will call this root dot right. Root dot right. This has got true from the D has got true from left. It will call this root dot right with 2 into I plus 1, that is 9. 9 will check, is I equal to null? No. Is 9 greater than 9? No. It will check for left and right. This check for left, it will hit the base case, return true. This I will get true from this left, true from right, because both are null. It will check return and, that means both has to be true. Both are true, yes, only then it will return true. Now D has got true from left, true from right. Here we have and, both has to be true. Okay, now B has got true from its left. Now B has executed this part. Now B will move towards root dot right. It will come over here at E. E will check E is not null, and here at E the index is, that is 2 into 2 plus 1, that is 5. Is 5 greater than 9? No. It will check for left and right. Both are null. It will hit this base case. E will get true from left, true from right. Here we have and. So E will return true above. Now this B has got true from left and true from right. Here we have and, so it will return. Now A has got true from its left. Now A will call this root dot right with 2 into I minus 1, that I is 1. 2 into 2 plus 1, that is wait a second, 2 into 1 plus 1 is 3. Now here it is 3. Now C will again check Is C null? No. Is 3 is greater than 9? No. Now C will do root dot left. Here it comes with 2 into I, that is 6. Here F will call root dot left. F has null both sides, so it will return get true from left and true from right. Here we have AND. Now F will return true back to C. C will do root dot right with 2 into I plus 1, that is 2 into 3, that is 6 plus 1 7. Now G has null both sides. It will hit this base case and get true from both sides. Since we have AND, so G will return true over here. C again has got true from both sides. Since we have AND, C will return true. Similarly, A also has true from both sides. Because of this AND, A will return true. And that's how we complete the recursion and we get the answer as true. And we can see that in this. I'll again draw this same tree again. Here we can see that this I've drawn this tree again for a clear picture. We can see clearly that this is a complete tree and we got the answer as true. So I've done a clear dry run as well as I wrote the code. If you still have any doubt, you can drop it in the comment box, and thank you for watching.